Okay, welcome back. So the idea for today is we need to finish our discussion with quotient spaces. And today I want to show you how powerful this construction is through examples. So before we get there, as format, I want to recall some things. Well, maybe the first thing I want to do, today we're going to work with quotient spaces. So uh, first thing I want you to recall is that we know how to suppose you have a set X, a topological space with a equivalence relation, then we have a quotient topology and we know how to construct or define continuous maps out of it. So if you want to construct a continuous map out of a quotient space, we can do so just using continuous maps out of X. So I'm really going to use this today with no much distinction between, or no much emphasis on what we already know. But I want to, in case you don't remember what I'm saying here, maybe go back to the last two lectures and see how we did things there. So not only we know how to construct, we also know if we call this function f and the induced function f tilde, so this is what we call f descends to the quotient. Now then, know how to decide if f is injective, sorry, f bar, or surjective. And we know it's continuous if and only if f is continuous, and also how to decide if it's open. At least when f is open, f bar is going to be open. So these are things I want to use today. Now, more stuff that I also want to use today that we didn't really mention explicitly before is also not new. If you have two topological spaces, so let's call them X and Y. Well, we say they are homeomorphic. So this is not new. If maybe let's put some names here, topological spaces X and Y. They're homeomorphic if there is a homeomorphism between them from X to Y. And very importantly, as I mentioned before, but I want to make this explicit, this defines an equivalence relation. An equivalence relation. So what do I mean here? In such case, if there is a homeomorphism, we denote instead of X equals Y, we say they are homomorphic. And this should mean topologically they are the same. In other words, you have a one-to-one correspondence between these two sets, and that correspondence and its inverse are both continuous. So I wanted to show this defines an equivalence relation, and by that I mean this relation is going to be always reflexive, meaning any topological space is homeomorphic to itself, just like identity. It's going to be transitive, and it's going to be symmetric. So we can, in some sense, use this as a sort of equality. Not really, and we know some very nice properties. And the last thing I want to mention before we start with today's examples is the product topology, because at some point I will use this. So the product topology on a Cartesian product of two sets. This has basis. Let's call this P sub product. which also coincides with what we call the subbox. And it's given precisely by subset of the form u times b, where u is opening x, b is opening y. So nothing new here. But something very important is if you have two functions, so exercise, and this we discussed before, if we have two continuous functions, f from x to y, and then you take some, let's call it g from x prime to y prime. If you have two continuous functions, then this map, the map, let's call this h from x cross y to x prime cross y, sorry, x cross x prime to y cross y prime, where for x comma y, where you should say x comma x prime, goes to f of x, g of x prime, this function is continuous. And this is a not complicated thing to show, but it's very useful for one of today's examples. Okay, let's just jump into them. For my example one, I'm going to recall something that we already discussed. So the kind of action of this example is quotient is not the same as the leading points. So quotienting out by an equivalence relation is not the same as the leading points in the space, and I want to explain that to you. So I first want to start with something we saw sometime before. So this is an example from lecture 12. Let's take a set. Just this closed interval, 0, 1, inside the real numbers with induced topology. So subspace. And we're going to define the relation on x, on the set x, by, we're going to say that x is rated to y if and only if x equals y, or these two guys live in 0, 1. So that's my definition of this relation. But to be honest, this is never important, because that's what you always want to include such thing in a, such thing on any definition of an equivalence relation. So the important thing is living here. So something that it's very important is that we can tell what the classes are here. So the classes for this relation are we computed them explicitly. So the classes are just going to be, well, that's what is not set 0, 1 quotient out by this relation. And these are just each singleton, because it's only related to itself. If it is not 0 or 1, maybe let's just say x is in the open interval, none of the extremes. But then 0 and 1 are connected, so they form their own, are related, sorry, so they form their own equivalence class. And the idea here is, or maybe before we continue with the idea, let's say that we also denote this quotient set by, instead of saying we're quotienting out by this equivalence relation, you can say I'm quotienting out 0, 1 by the set 0, 1 with two elements, because I'm taking these 2 points and just identifying them on the quotients. And I'm going to use this notation later today at the end of today's class. Okay, so what do we do here? We showed, what did we do? We showed that the map f that goes from our interval from S1, given by f of t is going to be just go around the circle, 2 pi t sine 2 pi t. Uh, this gives a continuous bijection. So what this map is doing is something like here's your 0, 1, you wrap them around the circle like this, counterclockwise. And then at 0, you hit 1 again. So this is your x, this is your quotient. And this is what this function is doing. So I started this class by talking about homeomorphisms, but so far I'm just saying that we are going to have a continuous bijection f bar from the quotient space 0, 1 over, maybe let's use this notation so that we get used to it, to S1. And this function is very close to being in homeomorphism, but we don't know that yet. So let me state this fact. This f bar is open, and hence homeomorphism. So what we're saying here is this function here. So this function I can write kind of explicitly f bar on the class of some x. Remember, I use phi of x to denote the quotient map. Is going to just be f of x. So this is just cosine psi. And then maybe like this. So what we're doing here is we're identifying this quotient space with some space that we know. Because if you have a homeomorphism, then the two spaces topologically are the same. So this is a powerful statement. And let me be honest, we could prove this with some work. Mostly what we need is somehow an inverse for the exponential map on this set, this open set. We could prove this, but I really don't want to do this. Instead, what I want to do is I want to leave this as a hanging fact, but it will be just a one-line proof when we study compact spaces. So it will become way easier after or when we study compact spaces. So I will actually give you proof there. So this is nonsense at this point, compact spaces, but you will see these are very, very useful. We'll develop some very useful tools that are particularly going to imply this function needs to be a homomorphism. Okay, so far the only thing that I did was identify this quotient space as S1. But the idea for this example, let me go up, was to show that quotients are not just deleting points. So here, what I'm doing is I'm not just deleting a point. I'm doing something else. So let me go back now to example of deleting a point. So this will now be lecture 8. There we discuss this function g from 0, 1, but now open at 1 to S1. Same rule here, t goes to cosine 2 pi t sine of 2 pi t. So same rule. But the thing is, since we're not taking 1, this function is a continuous bijection. And we kind of proved G is not open. So I gave you an idea, don't really prove. But again, what I want to say is another fact, there can be no homeomorphism. no homomorphism. So maybe let's say G is not open, hence not no homomorphism. And in general, there can be no homomorphism from this semi-open interval to S1. And this again will be, this will have to wait until quotient, compact spaces. So what I'm saying here, you can form the quotient of the closed interval 0, 1 by identifying 0 with 1, or you can delete 1, for example. And in the first case, what you get is a space that's homomorphic to S1. And second case, you get something that it's not homomorphic to S1. So that's what we're proving. In other words, the quotient, here you identify 0 with 1, is homomorphically or topologically different from just delete 1 point from base say 0 open at 1. And why is that? Well, because this is topologically S1, and this guy is not. So the upshot here is quotients are not the same as the leading points. These are different things. Okay, second example. Example 2, for example. And today, by the way, we're just going to have a bunch of examples, but you will see they will become very interesting. So this example, it's a topological space that you should, or you could call the real line with 2 origins. Okay, so the idea here is we're going to take this set. So our set X is going to be the reals times -1, 1. So this is a subset of R2. So we can just take the induced topology. Topology from R2. And when I say R2, we know distinction, I just mean the standard topology. So next step is define an equivalence relation on X. By the following. So the relation is just going to be given by the following. X, comma, -1, the pair X, comma, -1 is related to the pair X, comma, 1 for all X in the reals. So notice what I'm doing now. I'm being more vague with how I define my equivalence relations. I'm not saying X, Y is related to X prime, Y prime, blah, blah, blah. I'm defining it very explicitly. So what I'm doing here is let's do some drawings. So this is my X. I have a line, here is 0, at height 1, and here's the same line at height -1, say. Okay, so the thing is, I want this to be aligned with 2 origins. So this relation is not really okay. I need to do something different. I need to say, I want this for all real numbers that are not 0. Okay, so what this relation is doing is you have 2 lines, one at height 1, another one at height -1. And this relation is doing is something like, if you are any point, that is some point here, X, let's call it, and it's not 0, then you're going to get identified with the same point that's on the other level. So these 2 points get identified. Maybe I can use some color. These 2 points get identified, and then these 2 points get identified. These points get identified, and so on. Also this side, these 2 points get identified, and so on. But 0 Well, of those, you have two copies because you are not identifying them with anything. So the quotient here, quotient is going to give you kind of a maybe thicker line, something like a thicker line. Then let's keep space here. And that thicker line is going to have two origins because you never identify this point, that point with anything else. So now we have this space, our quotient space. This is X over this equivalence relation, and that's what we call the line with two origins. So here we have an open line, and of course you go forever and forever in that direction. Okay, now we should try to understand this space. So to understand this, I want to well, maybe let's put some names. So the space, the quotient space X over this relation is within quotient topology is called the line with two origins. Of course, the two origins are the class of the point we have 0, -1 on the line below, and then 0, 1 on the line above. Oops, sorry. And the class of 0. So remember the quotient space here is the collection of classes, so you have to classify. So now to show how powerful this quotient space construction is, I want you to remember when we studied Hausdorff spaces and first countable spaces. So I want to show you this quotient is going to satisfy one, but not the other. So claim one will be our quotient space, line with two origins, is first countable. And proving this will be an exercise. So let me give you a hint. Let's take the quotient map that we always have. So this is the surjective map that's pretty much defining the topology of the quotients. And the hint here, so of course this is an exercise. It will appear on the homework assignment at some point. And the hint here is, what's the idea? Why is it first countable? Well, we have something like this. We have the line here with two origins, and you have like the two lines here, 0 and 0. So what I wanted to prove is that if you take an open interval, A, B, for example, cross 1, so that means I'm taking an interval here. This is going to be open. It's always open in the quotient. And that's for any interval. Now, the reason behind this, you have to consider two cases, because in one case, your AB cross 1 will not intersect 0. So first case will be if 0 is not in the open interval AB, then how do we prove something is open? Well, the idea with this set, if it's here, it's going to look like this. Right? And of course, from A to B. So how do you prove something is open? You need to compute its preimage under phi. That's the definition of the quotient topology. So when you compute the preimage of this set, and you're claiming it's open, what you're going to have is, so you're here, you project with pi, but now you need to compute the pre-image. So what are all points in this space that will land here? Well, now you have two copies because these 2 points under pi, under the quotient, go to the same point. So the image here is going to be AB cross 1, but also -1. So you'll have both. And that's open in our X. On the other hand, if 0 is not, sorry, if 0 is in AB, so let me use maybe this color red, learn something like this situation here. Then when you project, you're going to be here. You are going to take this copy of 0, but not this origin. So when you project such thing, you will get this, you will get 0. Okay, that's pi. And now we want to compute the inverse. So we want to compute the inverse of pi of AB cross 1. So here, if you're here and you compute the pre-image, what you're going to have is, well, points that land here are, of course, these points. So we said it's going to contain AB cross 1, but it's going to contain more. It's going to contain all these other points. So it's going to contain, it's also going to contain AB minus 0 times 1. So this complicated thing is just this union of these two sets. In one case, in the case 1, you have to consider the entire family, and here you only need to consider these two things without 0. The 0 is not here. Okay, that's the hint. And claim 2, this will prove, is that the quotient is not Hausdorff. So this will be an example of a first countable space that is not Hausdorff. For example, that's not very easy to come up with unless you do like trivial things. So why is it not Hausdorff? We can prove our theorem that in an infinite space, you have this Hausdorff axiom, and sequences will converge to at most one point. So we'll prove that there is a sequence. Actually, we'll construct a sequence in our function space that converges to 2 different points. And then that will mean that space cannot be Hausdorff. And of course, these 2 different points will be the 2 origins. So what's the idea here? The idea is, we'll start with, so the idea is once again, this is what we have. We have the real line, sorry about that. Real line, another one. And now we go to the quotient, you have 2 origins. So I will start with the sequence. Let's call this xn, which is by definition 1 over n 1. So what I'm doing here is suppose this is 0. With my xn, what I'm doing is I'm just getting closer and closer to 0 on this line. Right? So since this sequence converges to 0, 1, it next, and the quotient space is continuous, we know that map is going to be particular sequentially continuous. So we know that phi of xn needs to converge to the class of 0, 1 in the quotient space. Okay, but that's not the only thing we can say. We can say something similar. So similarly, I will construct a second sequence, but here, and they will become the same sequence here. So yn is going to be the same thing, 1 over n, but by derivative. So this is my yn. I'm getting close to 0 on this line. Similarly, that sequence converges to 0, negative 1 in x. And again, phi is continuous. So it's sequentially continuous. And that means phi of yn will converge to, well, phi of 0, negative 1. And of course, you can apply phi to both sides of the limit. You will get the same equality. So what's going on here? Let's take a look at this. Here, you go to the function, you're doing something like this. But with these guys, when we go to the quotient, we're doing absolutely the same thing because these two things are related. So xn is not yn, but phi of xn is phi of yn. So since xn is related to yn for every n, what we know that phi of xn is going to be equal to phi of yn, because that's what the quotient applies. Okay, but then we have the sequence. So the sequence phi of xn, this sequence converges to this point 0, 1. But since it's also equal to this guy, also converges to 0, negative 1. And these two, so sorry, pi. Here, we need to say pi of these guys, the classes. But these 2 points are not the same. Phi of 0, 1 is not phi of 0, negative 1. Well, because they are not related. Because 0, 1 is not related to 0, negative 1. So the space cannot be housed. Not be housed. And that was our claim. Okay, the line with 2 origins. That was a very interesting example. And again, remember, it's not so easy to come up with such things. So spaces that are Hausdorff, not Hausdorff, but first counter. Okay, last example for today, example 3. This is a great example. It's called the torus. So the torus, let me tell you what it is, and then I will show you a picture of, hopefully I will convince you why these two things are the same, but we don't rely on pictures. So the torus is S1 cross S1. So what's the picture for this guy? It's the following. It's a donut. Well, I should say it's the surface, the surface of the donut, not the donut, solid donut. So why is this guy S1 cross S1? Well, I'll hopefully convince you of that in a moment. But another way of thinking about this is here you have circle, right? So this is the part that you cannot see. And at that circle is kind of copied, but it's not just copied on a line. In that case, you'll get a cylinder. It's copied on another circle. That's why you have S1 cross S1. So you keep moving your circle all the way around, or you should change curvature here. You keep moving it, but what you're actually doing is you're not just doing a cylinder like this. At some point, these two things get identified. So that's how you get the donuts. Okay, now let's try to understand this from our quotient space point of view. So this is going to be my space where I will define an equivalence relation, 0, 1 cross 0, 1. So this is a subspace of R2 with the standard topology. The standard topology. Okay, so here's the equivalence relation. Define equivalence relation on X by X comma Y is going to be related to X prime comma Y primes. I'm taking pairs because that's how my things in X look like. That's going to happen. They are related if and only if either X is X prime, but Y and Y prime are either 0 or 1. So that's one case. Or the other case you want to take is X and X prime both live in 0, 1, and Y is Y prime. So it's symmetric on the roles of X and Y. So that's the formal definition, but that's not how I think about it. Usually you can think about this in two different ways. So alternatively, what you can say is you're identifying X0, so I'm in this case, with X1, and this is for every X. And you're also identifying Y0, sorry, 0Y, with 1 for everyone. So this is what the equivalence relation is doing. And that's formal definition, but that's still not how people think about this. How we actually think about this, it's with a picture. So pictures of what we're doing. What we're doing is, here's our X. X is 0, 1 cross 0, 1. So that will be a square. 0, 1. So there you go. Now, how do we express this thing, this equivalence relation here? Maybe let's start with this part. So I'm saying X0 is identified with X1. So for example, this point is identified with this point. Similarly, this point is identified with that point. The only thing that's important here is that you live in the line. So instead of saying that, you say, well, I will identify this line with this line. So to be completely honest, these kind of arrows here are not very useful, but it's a very common notation because it's useful in some other settings. Okay, but that's not the only thing that we're doing. The idea is after you do this, you need to do something else. So I'll put a number here to remember that this is the first thing I do. After I do this, I also want to identify any point here with the same point here. But I want to do that throughout the line. And I'll put 2 arrows to remember myself this second thing that I'm doing. Okay. So in other words, here the blue thing is my X. And then I'm using some colors to express the equivalence relation that I have. So what I want to do now is, how do we go from the relation to our donuts? And here, yeah. So let's first do 1, and let's try to do 1. So when we do 1, what we'll do is we'll take this line to identify with that. So if you take a sheet of paper, you can visualize what's going on. You're joining like 2 borders of the piece, and that will give you a cylinder. Just the surface of the cylinder. That's where it becomes evident that you only have surfaces. So we're going to have something like this. this block will become a cylinder. I will make it longer because it will be easier to draw. So we're going to have something like this. Here's the part that we cannot see. We're going to have something like that. And to help me visualize things, let's say if this will be color, then I'll have some color here. And now my orange one will be kind of this segment over here. I should print this as one, and this is the direction I'm following. It's not important now. And now on the other side, these two will still be here. So I'll have a two going up on this side. If I wanted to, let me zoom in, I could also see if I want to remember it. Here I'm going down with two, but I don't need that. And on this side, I'll still have these two. So it's going. And again, I could have another one going the other direction here. And that's why sometimes having like these arrows become useful. Okay, so we're not done. Now we need to identify these two things. So we have like the two caps of the cylinder, and we need to put them together. And hopefully you can see after you do this, what you will have is maybe I can do an intermediate step. The intermediate step is the intermediate step is something like I will probably erase this, but at the end of the day, I'm trying to put these two things together. So I will kind of curve this, and this we're only in more than 2 dimensions to visualize things, more than 3 actually. So I need to curve this, uh, and you'll get something like this for the outer part, this for the inner part, something like that. From the continue this here, right? This you can see. Yeah, maybe let me make something better. So outer part, inner part. Here's my one. But at the end of the day, I do need to identify these two guys here. So these two guys need to be identified. So I need to keep going. And when you keep going, at the end of the day, you will identify the two extremes and you'll get our famous donut. So it's going to look like donut here, something like this. You have something like that. Maybe move this up. Something like this. Here's the donut. Here I will have my twos, and now they are together. So I don't have two copies of this because I identified them. Let's color this with gray so that you can follow it. And now one will go here, all around the stars, but it's mostly making noise. There you go. Okay, so that's how you get the torus. And now let me clean the intermediate step because it's not very nice. So that's our picture. And now here's the big claim for today. The claim is that our quotient space is homomorphic to S1 process. So remember, this means homomorphic. There is a homomorphism. Okay, how do we prove this? Let's recall some stuff from example 1. So this will be fundamental. So recall from example 1. What we have is we have a quotient map. Let's call this guy Q from the closed interval 0, 1 to the quotient space where I identify 0 with 1. So this is how I denoted that equivalence relation or that quotient space. And not only that, we proved we also have a homomorphism. Not only a quotient, we also have a homomorphism. From the quotient, where I identify 0 with 1 to S1. So the idea is now I will visualize this homeomorphism at each step here, kind of thing. But of course, it's going to be more rigorous than that. So now let's take 2 copies of Q. 2 copies of Q. So by the way, let's remember this map here, Q, is continuous. It's not just a map. And why is it continuous? Because it's a quotient map. That's how you would define the quotient topology pretty much. So let's take 2 copies of Q, get a map. Let's call this H from 0, 1 times 0, 1 to our quotient space times itself. So this is the quotient example that we did in the beginning of class as a reminder. So here I will take a point x, y. I will take it to q of x. Q, remember, is the projection q of y. And this map is continuous because of what I say at the beginning of class, which is continuous. Okay. Now we have this map, but we want to, at some point, construct the map out of the quotients of this space. And we know how to do it. So this is what we call that it descends to the quotients. So further, this H will descend to a quotient map. And why is that the case? So quotient, why is that the case? So the quotient is 0, 1 cross 0, 1. Quotient out by our relation on the square. And it's going to give us a map landing here. So why do we have such thing? Well, this is because of the following. Maybe let's call this map H bar. How do we prove this? In fact, how do we prove something descends to a quotient? We need to take 2 points which have the same image here and prove that they are mapped to the same map here. But that's just going to be not very easy, since Q of 0 is Q of 1. We know that H of example x0 is going to be just the same as H of x1. And why is that? Well, because if you do, here Q of 0, you will get the same as Q of 1. Okay, that's one thing we have. And also the same for y's. H of 0y is the same as H of 1y. So H will take things that are related to things that are, again, related. So these 2 things together mean that there is such a quotient map. So that there is such a quotient map. And the quotient map, since H is continuous, is also going to be continuous. So this H bar is continuous because H is continuous. So is H. So now, once again, we need to use this map that's coming from a quotient, from descending to a quotient. And we know how to prove it's injective or surjective. So going back to the first things we said today in class, first thing I would say is H bar is injective. And that will be H of x over y equals of H x prime y prime. That will happen certainly when x is related to y, but it's very easy to see that happens if and only if they are related. And then the second thing is that H bar is surjective. And that's because that's the easy one, because H is urgent. Hence, this H bar is going to be uh, bijective continuous. And once again, just to incentivize our study of compact spaces, we will see once again compact spaces that H bar is a homeomorphism. It needs to be a homeomorphism. So we don't need to prove the inverse will be continuous. That will be automatic once we understand uh, compact spaces. So what we proved is that the quotient 0, 1 cross 0, 1 by our equivalence relation is homeomorphic via our H bar to, well, 0, 1 quotient by the set 0, 1 times itself. So now each of these guys, coming from the first example for today, each of these guys is a copy of S squared. So our quotient space is the terms. Homeomorphically, topologically, sorry, using that homeomorphism is an equivalence relation, this guy is the terms S1 cross S1. And that's the last example for today. So mostly the idea was trying to convince you compact spaces are going to be very helpful. And also, doing this quotient construction, you get very interesting examples. So yeah, that's it for today. I'll see you next time. Have a nice day.